In this lecture, we learn about range space and null space. Let T be a linear transformation. T maps B to W. Then nullity or card T is defined by nullity T equals to x belongs to V such that T of x equals to 0 W. 0 W with a 0 element in W, this V and this W. Okay, then by the linear transformation T, x goes to 0, then the set of element which belongs to V goes to 0 by the linear transformation T. That set is called the nullity or card T. Let T maps R square to R square T of xy equals to 0 0 implies x plus y equals to 0 0. That implies x plus y equals to 0 and y equals to 0. That implies x equals to 0. Nullity of T equals to 0 element. Here as x0 and y0, so nullity T is 0 element, that is only the element in that form 0 0. As x0 y0, so nullity T only 0 0 element. Let T maps PR the polynomial space over R, which is infinite dimensional, to PR, polynomial space of R with infinite dimensional to polynomial space of R with infinite dimensional. Okay, defined by f dash x denoted by derivative of fx. We find now nullity T. What is the nullity T? If fx is a constant function, then derivative of f dash x 0. Okay, so f dash x equals to 0. Okay, therefore T of C equals to 0, where C is a constant polynomial. Therefore nullity T equals to all the constant polynomial. What is this? T be a linear transformation from the space of all matrices of 2 cross 3, order 2 cross 3, and to all the matrices of 2 cross 2 in the field of real number, defined by what is nullity of T. Now find the nullity of T. Implies 2a11 minus a12 a13 plus 2 of a12 0 0. That implies 2a11 minus a12 that equals to 0 and a13 plus 2a12 that equals to 0, which implies a12 equals to 2a11 and a13 equals to minus 2a12. So the elements of nullity are a11 a12 2k13 minus 2k1, that is the set k into 1 2 0 0 0 0 plus k1. So in nullity 2 there are two elements, which are then this and this. Therefore in nullity T these two sets are in nullity T. Next we defined range space or range T. T be linear transformation from V to W. Then range T or image T is defined by RT equals to y belongs to W such that Tx equals to y, x belongs to V. So range T be the subset of W and null T be the subset of V and this W. So x, this Tx, that equals to y. Such element y which belongs to W. Okay, so range T nothing but all the element of W which are the image of the element of V. Range T is nothing but the element of W which are the image of the element of V. Example, let the linear transformation be T maps P to R to M to cross to R, where P to R be the polynomial over R of degree most 2 with dimension of the space is 3, and this is the all the square matrix of order 2 over R, and T of f is defined by, so we find what is the range of T. Since the basis element of P to R be 1 x square equals to span, since this is a basis element, so we can find image of this element by this linear transformation, and since this is a basis element, so every element of this can be written as the linear combination of this. Okay, so if we find the image of this element, then the span of this element is nothing but a range of T. If we put that value 1, then this f11 minus f21 0 0 0 and f0 1. Okay, next if we put T of fx x, so T of x that equals to 1 minus 2 comma 0 0 0, so this element nothing but minus 1 0 0 0. Okay, and this element, what is this, x square, so x square T of x square that equals to 1 minus 4 0 0 0. Okay, so nothing but minus 3 0 0 0. Okay, this element are, therefore range of T equals to span of three time multiplication of this is this, so span of 3 element, the span of 2 element, okay, are equal, so we write R equals to this 1 0 0 1 be the basis of R2, therefore range of T equals to nothing but span of T of 1 0 that equals to 1 0 T of 0 1 that equals to, therefore range of T that equals to nothing but span of, so range element, range T of this are this. Now what is rank T and what is nullity of T? range T and nullity T are two subset V and W are vector space, so RT and nullity are subspace of W and V respectively. In this lecture we cannot prove this statement. Okay, I cannot prove here. Now rank T is defined by dimension of range T. Okay, rank T nothing but is dimension of RT. So and we written rank T equals to dimension of range T equals to dimension of image T, and nullity of T is defined by dimension of nullity T. Okay, okay, okay. So T equals to dimension of nullity. Now we define the concept on one and on two. What is the on one? If T be a function or mapping, T is called on one if T of x1 equals to T of x2 implies x1 equals to x2, and T is called on two if there exists y belongs to W such that Tx equals to y. Then T is called on to, that is every element of W where T maps V to W. If T be a mapping from V to W, every element of W has its pre-image, then this mapping is called onto. And to distinct element x1, x2 goes to T of x1, T of x2, and this not equals to, so that implies not equals to. Then the mapping T is called on one. Let T maps V to W be a linear transformation. Then T is 1 to 1 if and only if nullity of T that equals to 0. If nullity T contains single 0 element, that is there does not exist any non-zero element in nullity T, then the linear transformation T is 1 1. Proof: T is 1 1, x belongs to nullity of T, then T of x that equals to 0, that equals to T0. Since T is 1 1, so x equals to 0, because every element has a unique image. If tx1 equals to tx2, then x1 equals to x2. So tx equals to 0 implies t0 equals to 0. So only possibility is x equals to 0. Now nullity of t equals to singleton 0. Then we prove t is 1 1. Suppose tx equals to ty. That implies tx minus ty, t of x minus y, by the property of linearity, that equals to 0. Therefore x minus y belongs to nullity of t. Since t of x minus y equals to 0, so x minus y belongs to nullity of t, but nullity of t equals to 0, therefore x minus y equals to 0, which implies x equals to y. We choose tx equals to ti, which implies x equals to y, therefore t is 1 1. Now define rank nullity theorem. What is the rank nullity theorem? Let T maps V to W be a linear transformation and V and W be finite dimensional. Okay, here finite dimensional. Then dimension of V, that equals to rank T plus nullity of T. This is called rank nullity theorem. T must V to W be a linear transformation, V W finite dimensional, then dimension of V equals to rank of T plus nullity of T. If only V is finite dimensional, then also this theorem is valid. Let T maps V to W be a linear transformation. Okay, V and W be, let T maps V to V be a linear transformation and V be finite dimensional. Then the following are equivalent. What is that? A, T is 1 1, B, T is 1 2, C, rank of T equals to dimension of V. These three are equivalent. A implies B, that is T is 1 1 implies T is 1 2. Since T is 1 1, nullity equals to 0, therefore dimension of nullity T equals to 0. Therefore by rank nullity theorem, dimension of V equals to dimension of RT plus nullity T, that equals to rank T plus 0. Therefore rank T equals to dimension of V, that what implies dimension of range of T, that equals to dimension of V, that implies range of T, that equals to V. Therefore T is 1 2. B implies C by previous proof, and C implies A. If it is 1 2, then RT equals to V, therefore dimension of RT equals to dimension of V, therefore rank T equals to dimension of V, that is by rank nullity theorem nullity T equals to 0, hence C implies A, obviously proof. In this theorem obviously T be a linear transformation. If T is not linear, then we cannot say. If V is not finite dimensional, then it does not follow T 1 1 then T 1 2. Example, PR to PR, polynomial space over R, infinite dimensional, T of fx that equals to 0 to x ft dt. Now T of fx that equals to 0 implies fx equals to 0, and the properties of continuous function, this integral is 0 if fx equals to 0. So nullity of T equals to only 0 element, Therefore T is 1 1. Therefore T is 1 1, but T is not 1 2. Since 1 belongs to pair polynomial, or every constant polynomial belongs to pair, has no pre-image in that polynomial, because there does not exist any polynomial belongs to pair whose integration is constant, where at 0 to x, but 1 has no pre-image in polynomial space of R, because there does not exist any fx belongs to pair such that t of x is to 1. Therefore t is not 1 2. T is 1 1 does not imply t is 1 2. Here v is not finite dimensional. Some use of rank-nullity theorem. Let T maps R3 to R2. Nullity of T equals to x such that Tx equals to 0. T of A1, A2, A3 that equals to 0 0 implies A1 minus A2 equals to 0 and 2 of A3 equals to 0. Therefore A1 equals to A2 and A3 equals to 0. Therefore nullity of T equals to A1 0, that equals to span of 0. Therefore dimension of nullity that equals to 1, only one element, so dimensionality equals to 1. Therefore by dimension of R3 equals to dimension of nullity T plus dimension of range T, there that implies this is 1 and this 3 equals to 1 plus dimension of range T, that implies dimension of range T equals to 2, that equals to dimension of R2. Therefore T is not 1 1 but T is 1 2. In this lecture we will learn the definition of range space, null space, rank T, nullity T, and some theorem based on rank and nullity T. Here we stop.